morning, Prof. Riando.
Good morning. Can
How
you
are
hear
you
me?
today?
Good morning.
How are you today, Prof?
Okay, wait a moment. Okay, yeah. So, can you hear me now?
Yes, we can hear. Very
Yes.
clear.
Okay.
Okay, yeah. Because the voice is a little bit low, and my internet connection is not good enough.你是勇气，你碰来健康。勇气，或者是你帮我帮你改这个拜托。
Laboratorium riset kimia didedikasikan untuk kegiatan penelitian, baik untuk dosen maupun mahasiswa.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Tohari, laporan lab riset kimia. Nah, sekarang saya berada di ruang instrumen yang bernama AAS. AAS ini merupakan alat yang digunakan untuk analisis logam total.
Salah satu instrumen yang dimiliki laboratorium kimia yaitu adalah spektrofotometer inframerah atau yang biasa kita sebut dengan FTIR.
Izin.
Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, saya Aprisilia Rizky Wijaya dari Laboratorium Kimia Terapan jurusan Kimia. Untuk hari ini saya akan menjelaskan sedikit tentang alat potensiostat yang ada di
Hati-hati ya, Sil.
Selamat datang di Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Islam Indonesia. Laboratorium riset kimia didedikasikan untuk kegiatan penelitian, baik untuk dosen maupun mahasiswa.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Tohari, laporan lab riset kimia. Nah, sekarang saya berada di ruang instrumen yang bernama AAS. AAS ini merupakan alat yang digunakan untuk analisis logam total.
Salah satu instrumen yang dimiliki laboratorium kimia yaitu adalah spektrofotometer inframerah atau yang biasa kita sebut dengan FTIR.
Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, saya Aprisilia Rizky Wijaya dari Laboratorium Kimia Terapan jurusan Kimia. Untuk hari ini saya akan menjelaskan sedikit tentang alat potensiometer yang ada di laboratorium.
Mahasiswa semua loh.
Tes. Kedengeran ya? Oke. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
First of all, let us pray to Allah Subhanahu wa Ta'ala for His blessing and mercy. We can join this event, Studium Generale, with the title Research in Chemistry of Progress and Motivation. Second, let us greet and pray to Prophet Muhammad Sallallahu Alaihi Wasallam, who has brought us to the light path and left to the dark path. Okay, the Honorable Professor Rianto, PhD, as the Dean of Faculty Mathematics Science of Islamic University of Indonesia, the Honorable Professor Dr. Isfatimah as Chairman of Chemistry Department, the Honorable Dr. Radlis Alwar PhD as Chairman Master of Chemistry Study Program, the Honorable Professor Medelvet audience from Indonesia and abroad. Okay, let me introduce myself. My name is Salma Haminati. I'm one of lecturer in chemistry department. Before we will in the main agenda, let me tell you of the structure this agenda today. No, first, opening. Second, we will have the reading Holy Quran by Cecep Sakbana Rahmatillah. Then the third one, we will have opening remark from the Dean of Faculty Mathematics and Natural Science, Islamic University of Indonesia. Then we will in the main session, which is the talk from Professor Rui Andong. Next, we will continue with discussion. Then we will have the second lecture from Dr. Andes Alvar, PhD, with the topic of research in Master of Chemistry study program. Then we will have discussion, and then we will have closing with the announcement of door prize. Okay. So before we start, let's we open this. Next, I would like to invite Mr. Cecep Sakbana Rahmatillah to read the Holy Quran. To Mr. Cecep Sakbana Rahmatillah, time is yours. Okay.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
A'udzu billahi minasy syaithanir rajim. Bismillahirrahmanirrahim. Ya ayyuhalladzina amanu dzkurullaha dzikran katsira. Wasabbihuhu bukratan wa asila. Huwallazi yusalli alaikum wa malaikatuhu liyukhrijakum minadh dhulumati ilan nur. Wa kana bil mu'minina rahima. تحيتهم يوم يلقونه سلام وأعد لهم أجرا كريما. يا أيها النبي إنا أرسلناك شاهدا يا أيها النبي إنا أرسلناك شاهدا ومبشرا ونذيرا وداعيا إلى الله بإذنه ورسولا منيرا وبشر المؤمنين بأن لهم من الله فضلا كبيرا. Sadaqallahul azim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thanks to Mr. Cecep for reading Holy Quran. Next, we invite Professor Rianto PhD to give the speech. To Professor Rianto PhD. Time is yours.
Okay, thank you to Salma. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, selamat pagi, ladies and gentlemen. Alhamdulillah, this morning we can join for this event, Studium Generale by Department of Chemistry, Faculty of Mathematics and Natural Science, Islamic University of Indonesia. The honorable speaker this morning, Professor Rui Andong from National Tsinghua University, Taiwan. The Honorable Head of Department of Chemistry, Professor Isfatima, and then the Honorable Head of Magister Chemistry Study Program, Pak Alwar PhD, and all participants this webinar. Alhamdulillah, this morning has joined with us in Zoom more than 100 participants. Welcome to new student, Chemistry and Magister Chemistry Study Program, Department of Chemistry. Thanks a lot for Professor Rui because help us in many activities, such as seminar and then clinic for paper, joint publication, and other activity. This morning, we will discuss with Prof. Rui about research topic in chemistry, and I hope this activity can increase motivation our student to research. Research topic in chemistry in Indonesia focus on environmental issue and then treatment of waste with many method and material, and then renewable energy, new material with nanoparticle scale to many application, and then essential oil, oxygen for COVID-19, And then today we have developed treatment of infectious disease from COVID-19 and other topic. Research must be able to be used for the community and provide to rahmatan lil alamin. Finally, I hope this event successful and then all participants can enjoy discussion with Prof. Rui. Thank you very much and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Pianto PhD for his speech. Okay, we continue in the main session of this event. Next session, I will give this to the moderator. Okay, before this main session, we want to have photo session. So please prepare your video. Okay, thank you.
Morning, Prof. Rui, Prof. Dong. How are you?
Okay, we will take a picture for today. 1, 2, 3.
Beacon is not clear. I'm sorry.
Once again. 1, 2, 3. Once again. 1, 2, 3. Thank you.
Thank you very much.
Mr. Rianto, nice to meet you.
Yes, nice to meet you.
Yeah, nice to meet you. Yeah.
Okay. Next, we will have the main session of this event. So before we start, Director, to Dr. Maisari Utami, that is yours. Thank you.
Thank you. Good morning, everyone. Especially would like to thank these Riantos and chairs this Madibas for the invitation.
Yes, I'm sorry, Mr. Excuse me, Prof. Dong. Your sound is not clear.
Really?
Sorry. Yes, Professor Rian.
How about
your sound
the case now?
is not clear.
The case now? No.
Please you try, Prof.
Actually, okay, I can try to you.
Yeah, no worries.
How about the voice now?
Yes,
Okay,
yes,
clear.
yes,
Today.
clear
Yes.
now.
Okay, so that
I'm sorry, Professor Rian. I'm sorry.
Yeah.
I will be the moderator for your
Okay.
session.
Yeah.
Okay, I'm sorry. Okay. Okay, thank you very much, Mrs. Salma Aminati, PhD. Hello, good morning, Professor Rian.
Good morning.
Okay, how are you?
Quite good, thank you.
Okay. Is it okay now to start the lecture?
Okay, yeah.
Okay, yeah.
So maybe
Let
I
me-
can share my screen.
But first, maybe I will introduce you first, Professor.
Yes.
Is it okay?
Okay, please.
Yes, thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen. Selamat pagi in Indonesia. Good morning in Taiwan. And Welcome Professor Rian Dong in this virtual event of Studium Generale organized by Department of Chemistry, Universitas Islam Indonesia. Warmest greetings from Yogyakarta. So ladies and gentlemen, today we have our esteemed guest speaker, Professor Rian Dong from Taiwan, who will deliver lecture about reason in chemistry, progress and motivation. So it's very interesting topic, and it is my pleasure to be a moderator for this lecture. So my name is Maisari Utami. I'm from Department of Chemistry, Universitas Islam Indonesia. Before we start the lecture, I'm glad to briefly introduce our renowned speaker, Professor Rian Dong. So let me share the screen first. Okay. Yeah. Professor Rian Dong is a full professor in Department of Medical Engineering and Environmental Sciences, National Tsinghua University, Taiwan. He graduated bachelor degree in Department of Environmental Engineering, National Chung Sing University, and continued his master and doctoral programs in Graduate Institute of Environmental Engineering, National Taiwan University. Some of his current resources are electrochemistry, environmental remediation, environmental nanotechnology, sensor, and biosensor. And based on his Scopus data, he has published over 200 papers with citation over 7,000 and H index of 55. He also has so many high reputations. He received International Honorable Member in 2016, Outstanding Research Award in 2015 and 2008, and Most Cited Paper in 2006, and so many else. Now, Professor Rian, please present your topic in 90 minutes, and we will have around 15 minutes for discussion session. Now, ladies and gentlemen, please give warm welcome to Professor Rian Dong. For Professor Rian, the time is yours.
Okay, thank you, Dr. Utami. Thank you for your nice introduction. Yeah. Okay, let me share my screen. Okay. So now, can you see?
Yes.
Yes, clear, Prof.
Okay, so if you can see names, that would be perfect. Yeah, because the nouns are actually I changed the system a little bit. So this is the first times I use this system. If you cannot see the change in screen, please tell me immediately. Okay, yeah. So today I would like to talk about the topics that is very interesting, I think. Yeah, I would like to talk about the recent research in chemistry, especially the progress and motivations. I'm Randall from Tsinghua University, like the Dr. Utami introduced. On the outline today, I would like to introduce including 5 major parts. The first one actually is the motivation. Why we need to do the research, especially in the fields of chemistry. So the most important issues worldwide by 2050s we need to know. Actually, they only have just 2 or I cannot say 2, several things. One is the net zero emission. Second is the water challenge. Third one is energy. So we'll just tell you why it's very briefly. Names will also very briefly to tell you what can chemists do, especially for chemists. Names I would like us to focus on the water energy methods, especially for the photocatalysis. During these topics, I mainly focus on the nanomaterials that can be used for photocatalysis. So that's the way I would like us to introduce you several different kinds of the types of the photocatalysis, including Chucky junction, PN heterojunction, or S scheme, and Z scheme, Z scheme. And would also like us to introduce you a very recent developed and very important case. We call it the photoelectrochemical reaction, PC. So hope that you will know that the recent progress in chemistry. So let me further just to know what is the most important issues by 2050. I believe that you guys know a lot that related to SDG. So from the UN, you always will know that the most important issues from UN is one is the climate change. Second is that they talk about energy. Third one is food, because we have a lot of the population. At this moment, we have around 7.9 billion population in the world. And estimates that in 2050, we have 9 billion of population in the world. So people need to eat. So food is very important. Not just only for food, but they also need water. They also need energy. So it is very important. But all these three things, food, energy, and water, actually they are highly influenced by climate change. So that is why UN always focus on these four issues. But when we talk about the ecosystem of the Earth, okay, yeah, the most important elements for the Earth, actually, the first one is energy, because energy flow every day. A name that they are to the energy conservations, okay, on the Earth. So when we change to heat, when we change to carbon, when we change to different kind of things, all are related to energy. Second is water, like I mentioned for UN, people need to drink. Every day we need to drink the 2 liters, okay, 2 liters. And third one is the materials. That means that biogeochemical cycle and some others. But we have very limited natural resources on the Earth. For example, like those metal, carbon, and some others. So that's that they all are doing the cycling on the Earth. And fourth one is carbon. We need to eat a name from the organic carbon and to inorganic carbon. That means that's from the foods into carbon dioxide, or names from the forest or from the tree. They can convert carbon dioxide into organics. Names are some animal will eat the weeds, will eat the tree, some vegetable, and the name becomes that their body waste and become the meat that we eat, and the names inside our body, and the names again into the carbon dioxide. So that's when we talk about the most important issue raised by the UN for topic. And also think about the most important elements on the Earth, also 4 elements. When you do the interaction and names, we definitely will know that water and energy is the most important issues in the world. And from the water energy issues in the world, and names, we need to focus on 2 things. One is the 2030 Sustainable Development Goal. That means that SDG. It is also very important for human beings, especially this is the goal from the UN. Second is that we need to know 2050 net zero emission. Okay, yeah, so that is the most important issue by 2050 at this moment. Okay, so when we talk about the water energy methods, what is the relationships between water energy methods and SDG? Definitely from the UNEP, they have the 17 SDG goals. For example, no poverty, that's highly, or no hunger, that's highly related to food. But you can see that's from the SDG 6 and SDG 7. They talk about clean water and sanitation. This is for water. 7 is affordable and clean energy, that's highly related to energy. names, you can see that's the climate actions and that's the life below waters, the life on Earth, and some partnerships for the goal. All this actually is talk about the international cooperation for climate change. So you always will see that it is very important at this moment. And for Asian country, clean water and affordable clean energy actually is one of the most important issue at this moment. So that is why we talk about. Second is that's the net zero. Net zero actually is we can separate into several tiers. Tier one definitely is that tries to control the emission of carbon dioxide from those company, factory, and some others. If you can control the emission of carbon dioxide from company, factory, that will be fine. But we still have a huge amount of the carbon dioxide in the air. So that we still need to remove the low carbon dioxide from the air directly. So that's for the net zero emission. Actually, that includes the two things. One is that's to control the emission of carbon dioxide to the atmosphere. That is the first. Second is the tries to remove the carbon dioxide in the air at this moment. Okay, to the ground or becomes some available resources like fuel, like a tree, or we just store it. So net zero emission usually means that's the net zero carbon or the greenhouse gases emission. Not just only for carbon dioxide. Okay, I believe that's in Indonesia you have a lot of trees, so that will be good for you. But you also have a lot of petty fields. Okay, to cultivate the rice and some others, and also have a lot of cows and them. So that is the case. Names that means that they will produce the different kinds of greenhouse gases like methane, nitrogenous oxides, or even some others. So we would like us to do that is that we need to control is in integrated way. So a lot of people try to talk about the net zero emission is the carbon farming. It means that's like this one. We have the natural ecosystem, and then we have tree, we have animals, we have the lands, and we have some soil. So that's we can try to capture carbon from the atmosphere into the tree or into the farm or into the soil. So that is the case. So from the any kinds of the city, for example, like the Taipei city or Jakarta or Yogyakarta. So that's we will produce a lot of foods and the names. Most of the time we will dump the lost waste. And names we can do the bioprocess or tries to do the composting or tries to do the circular economy. A name becomes another food or become another available products. That is the case we can try to do. And it is also good for net zero. So for net zero emission by 2050, actually they include a lot of things, not just only for the removal of carbon dioxide. We can try to recycle the foods, we can try to recycle agricultural waste, we can try to do the carbon management and names. We can and try to contribute ourselves to net zero emission. So net zero emission actually is very important for a chemist at this moment, because we can do a lot of things, not just only to try to avoid to eat meat and some others. Okay, yeah. So from the IEA, International Energy Agencies, okay, they have a strategy for net zero emission here. So that's from the now 2021, they have some plan names to 2025, 2030, 2035, 2040 till 2050. So that they hope that that's all emission from the building, from the transportation, from industry, from electricity, and from others can try down to the zero. Here I just highlight some parts that is very interesting and also highly related to chemistry. For example, in 2030, 60% of the global car needs to be EV car, means that that's to be have the electric vehicles. And most of the new clean technology is the highly related to chemistry. In heavy industry, needs to have the scale has to be demonstrated at scale. That means that that's in 2030. In 2030, most industry needs to have their clean technology in their company. It is the huge amount of the opportunity for chemists to do, because the lost clean technology needs chemistry inside. And 2040, you will see that the needs to do the net zero emissions electricity globally. And 2050, almost the 70% of electricity green generation should be green. Actually, all this is highly related to chemistry, like I mentioned. Okay, so here is the strategy we can do for net zero emission. The first one is energy efficiency. It is not related to chemistry. That's the highly related to mechanical engineering or some others, because they need to do some works to improve the efficiency of engine and or some other machines. But second is highly related to chemistry. Sustainable and renewable energy, no matter we talk about wind energy, hydrogen energy, hydrogen production from waters, or hydrogen production from fuel and some other, solar energy also. Bioenergy definitely is the case for chemistry. Capture of carbon dioxide depends. Okay, we can talk about the carbon dioxide captures, storage, utilization. Carbon dioxide capture is also highly related to chemistry. Carbon dioxide utilization means that we convert the carbon dioxide into some green fuel or green products like methane, butanol, and some others. All this actually is the chemistry work. Carbon dioxide removal, that means that's the CDR, is also one kind of the works now highly related to chemistry. A lot of people try to cultivate algae, and then tries to use algae to remove the carbon dioxide from the atmosphere or from the carbon sink, like I mentioned, from the carbon sinks. Okay, I mentioned what is the carbon farming. So that is also highly related to chemistry. So from this introduction, you always will know that chemistry can do a lot in the future, especially you have I believe that you have the motivation tries to find, because it is important for any countries in the world or any institutes in any countries to do the research. Okay, yeah, so that is the case. We talk about a lot of net zero emission SDG, and we also mentioned that the water energy actually is very important. Why water is so important? Okay, I always use the slide to show the importance of the global water challenges. So that's maybe someone has seen it before, but I would like us to emphasize. Once Nobel laureate Richard E. Smarty, he mentioned in 2003, he raised the 10 humanity's the top problems for the next 50 years. And the first is energy, second is water, third one is food. That actually is very important for UN. Also very important, he raised. So that's in that case, we always will know that's why water is so important. You just see here. Okay, when we talk about the global water balance, that means that's their amounts, their mass. Okay, so you can see that the seawater has the 97.5% in mass. Names we have around the 2.5%. 2.5% is the frozen fresh water or underground fresh waters. So 97.5 plus the 2.5 means 100%. So that means that's all the available water resources we can see on the surface water. For example, like Mekong rivers or some reservoirs or some rivers or some stream. Actually, their total amount is the less than 0.01%. You also are chemistry. So that's I always try to say that if we talk about the total amount of the mass in the earth is 1 liter, of our waters. Okay, 1 liter. That means that we take a beakers. Okay, 1 liter. A name's full of water. A name's what is the percentage of the lost available waters for human beings? Actually, let's name 1 drop. Okay, so that's you have the 1 liters. You have the 1 liters of the water in the beaker. Names if you use the pipette for any kind of the pipettes, 1 drop actually is the 0.05 milliliter. Sorry. Okay. That causes a big problems for us because we have the 9 billion person, and only can use 1 drop of the water. Okay, so water is very important. Most worse is that because of the climate change, so that's the water quality as well as the water scarcity is very, very serious at this moment. So that's now we try to use the nanotechnologies to do. So that's from macros to nanos. That is the case. We can try to think about to solve the problem. Like since Rental mentions that's we need us to use the nanomaterials to solve the problem. Okay, in the real environments, the pollution is quite visible and perspectives. Actually, we can see that's the macro case, so that we can see the water discharge. We can see the color changes in the rivers. We can see a lot of garbage, a lot of pollutions on the rivers. So that is the case. So now we would like us to see is that's from macros to nano or from networks to in situ. It is very important for us to think about if we can do that from macros to nano and names we can use the very small amounts of our catalysts names we can solve the problems. A name that will be more efficiency, and names will reduce the emission of carbon dioxide and also will increase their treatment efficiency. So it is truly green. Okay, I mentioned is before what can chemists do. So that's here you always will know that we have a lot of element here. Some element has very good optical property. For example, okay, copper, silver, gold, they have some quite a good optical property. We have a lot of elements that has the very good electrochemical property, like a nickel, like a palladium, like a platinum. They all will have the very good efficiency for that. We also can have some others element quite good for dopant, like vanadium, irons, or some others transition metals. Okay, yeah. So that is the case. We can try to see. So for a chemist, the most important is this periodic table. Okay, here we can see that carbon is here, and the names, the silicon is here, names we can see some other phosphorus is here, vanadium is here, titanium is here. They all can form the 2,6 compound or 3,5 groups chemicals. All this actually is quite good for materials that we can use this to degrade chemicals. Okay, yeah. So for that case, areas of chemistry, I also mentioned it again. Okay, we will talk about the full energy water methods. So that's the for those water energy methods of the talk about the food, talk about energy, talk about water, talk about climate change, even talk about the carbon. Okay, all is highly related to chemistry, energy and environment. Okay, medical and health. Okay, lifestyles or science and technology. So that we can do that's the for environmental science and technology. Very important. Okay, water is one of them. Carbon dioxide is one of them. Energy is also one of them. Material science and engineering is also one of them. Belongs to the most important issue. Food chemistry definitely belongs to the chemistry, and some cosmetics and some others that they sorry. Okay, they are still the same way. Okay, yeah. So like I mentioned, since we would like us to focus on the water energy of foods, names that we need us to do it from the macros to nano. So that's the now we need us to do the environmental nano materials. Why needs the environmental nano materials? Okay, just think about we use a lot of materials in our daily life, especially in the treatment process. We use the membrane, we use the activated carbon, we use the resin, we use the sand, we also use the catalyst, MBR, deluxe, the desulfuration, and LP process. Okay, those material actually is the commercial products. Commercial product is quite good, but that they only can do for traditional treatments purpose. If we have the different kinds of the pollutants, and then we would like us to do different kind of things, and would like us to increase their treatment efficiency, then we need the good material. So we need to do it for customized material. So we need to prepare our own materials with tunable and controllable properties. It is very important. For example, it is the membrane we use for RO. So that's they just do it commercial. If we would like us to do the multifunction, and then we can try this to cause some nanomaterials, some nanoparticle on the surface to enhance their removal or clean efficiency. That is the case. This is the supposed for air control or air pollution devices. So that's we can try this to put some nanomaterial on the surface or inside the pole. So that's when the gas pass through this filter and names that they can be clean. We also can use this in water. So that's something like here. So that's we have some pole inside, so that we can put some very tiny particle nanomaterial, maybe just their particle size, maybe just only 10 nanometer or even 5 nanometer. And then when water passes through, then the names that they can remove some pollutant and tries to clean, even those we can recover energy. So that is the case that now we would like us to do. So that's one of the most important case. One of the most important cases is to try this to fabricate the photocatalyst. Why we need the photocatalyst? Because the sun is the main energy source of in our world. Okay, yeah. So every day we receive the energy from the sun. Okay, they will be there. Okay, at this moment, they will be there, and then try to provide the constant energy for us every day, every minute. So that's we can try to use the energy of the sun to degrade chemical and elements to convert energy. It is very important. It is very important for chemistry. So that's for the photocatalysis. We definitely need some material. Okay, so we can try to see is that they can have divide into three category. One is that tries to do the direct photocatalysis, tries to use the solar light to decompose. In this case, maybe you don't need the photocatalyst because they can use the solar light to decompose chemicals directly. Second is the dye sensitize the photocatalyst. It is the case here. When you see that they have some dye here. So that's when you have the semiconductor of the material here, for example, like a TL2, and names when they receive the light, okay, and names that they can irradiate electron from valence bands to conduction band, and then transfers the electrons to the dye. So dye will do some electron transfer and names that they can do the photo reaction. It is also quite common. For example, the solar cell is something that this way. So solar cell actually is one kind of the photocatalysis reaction. So a lot of chemistry inside and a lot of chemists can do that. And the third one is that the case we would like us to focus today is the heterogeneous photocatalysis. Means that we need to use the photocatalyst to decompose pollutant as well as to produce energy. It is the case. We can use just one photocatalyst, or we can use the two, or even we can use the three together, and names that tries to make the efficiencies that are very good. Okay, yeah. So that is the case here. So maybe you know that the photocatalyst, maybe you have this idea. So that's I would like us to introduce you very fundamentals of the photocatalyst. This is the case we talk about is the photocatalyst. Most of the photocatalyst is the semiconductor. Okay, we also mentioned that what is the semiconductor. When for semiconductor, they will have the band gap here. And when they have the band gaps, the name that they will have the valence band and conduction band. They always can receive the wavelengths. When the wavelengths that they receive can irradiate the electron from valence bands to conduction bands. Names we call this one is the electron transfer or charge transfer. Also, so that's here will produce hole. And electrons will be here. So that's that there has one electron and one hole here. Definitely that they will be compact. The electron will be compact into from the conduction bands to valence band. And we call this one is the recombination. But at this moment, we don't talk about that case now. Okay. So that's after the photon reaction, we can produce hole and electron. Electron actually they can transfer to the surface to some other material or directly to the acceptors. So that's the acceptors will become the A- radical. And the hole will also transfer to the surface. And names that they will be here and names that they will oxidize some donors. Okay. So that's the for hole. We call this one the material or the chemicals can receive the hole. We call this one is the donor. And for electron, the chemicals can receive electron. We call this one is the acceptor, so that they use A and B. So hole will react with the donor and then become a radical. Electron will react with acceptor and then becomes the radical. This radical is very important because the radical reaction is the key reactions for photocatalysis. Okay, also for photocatalysis. So this is some example, not all, but only one example. Photocatalysts, when they receive the light and produce hole and electron, names that they will try to react with some donor. A name, for example, water is one kind of donor and will produce hydroxyl radical. And names whole will also react with the hydroxyl ion, become hydroxyl radical. Names they also can directly react with protons, becomes the others intermediate. And electrons that can react with oxygen becomes the superoxide anion radical, and names to produce peroxyl radical. So that's all this actually is the chain reaction for radical. So if you have the proton inside, the names that they can decompose very fast. So that's that you can try to clean it. Okay. And the other case is that they will try to produce hydrogen gas here. Okay, we'll talk about later on. And the advantage here is that the reaction will be very fast because they can produce a lot of radical. Conversion efficiency will be good. Okay, also because of the radical. They can operate under normal condition. You don't need to change the pH too much. Names just under the room temperatures because you need to use the sunlight that can provide quite a good energy. So that is the case for the photocatalyst, the PC with the light names that they can try to produce a lot of radical. So that's here you can see that they can do a lot of things. Okay, from car, air purification, water purification, medical applications, agriculture, and some others. They also can try to gain energy, water splitting for hydrogen evolution or energy conversion from the solar cell. So photocatalysis actually is one kind of the most important reactions in chemistry. A lot of people would like us to do that. Okay, yeah, okay. Especially when we talk about the energy and environment names, it is the mass for photocatalysis. So that's it's just too a little bit slow. Okay, so we talk about the photocatalysis. A name for the photocatalysis, we need the photocatalyst. For those photocatalysts names, we all say that's the semiconductor. So we would like us to define what is the semiconductor. We use the difference between the valence band and conduction band. This is the case in the environment or in material science and engineering. In chemistry, okay, we call this one is the HOMO. This one is the LUMO. So that's the valence band equals to HOMO. Highest occupied orbitals, okay, HOMO. Okay, CB, conduction bands equal to LUMO, okay, lowest unoccupied molecular orbital, okay, yeah, so that is the case. So that will be makes you a little bit comfortable if you do not have ideas about the valence band and conduction band. Actually, it's the HOMO, LUMO, okay. So every semiconductors has their valence band and conduction band. If the valence band and conduction bands is in between 0.2 to 4 electron volts, then we call this one is the semiconductor. Here is the case. For the valence band and conduction band, we can find that there's redox potential here. So that's this is the volt. And why is the case we talk about the band gap? Okay, sorry, I forgot to mention. Between the valence band and conduction band, we call this one is the energy gap. Gap of the energy. So that's if you like to that electron jumps from the valence bands to conduction band, you need to give names energy. So UV light or visible light or any kind of light that can irradiate, that is good. So we call this one is the band gap. So that's for this band gap, that's the will be the most. But you just that one electron transfers from valence bands to conduction band. So one electron tries to overcome the band gap volt. So that's the band gap is the electron volts. That is the case. So that's here is the volts, and here is the band gap. So it becomes the electron volt. That is the reason. Okay, TiO2 is the 3.0 to 3.2, and iron oxide is the 2.1. It is very important Cupric oxide is also one case of the case we would like us to use that in between 1.9 to 2.2. Okay, tin oxide that we have in between 3.4 to 3.8. Zinc oxide is similar to TL2. Okay, that is the 3.2. So that's, you can see that's the for the TL2 and zinc oxide. There's conduction band and valence bands position are almost the same. So that's we seldom see people to merge these two together, but they can try to merge the zinc oxide and tin oxide or the zinc oxide to some others. And a lot of people also would like us to use the graphitic carbon nitride. They have around the 2.7, but the valence band and conduction band will change. Okay, this one is the bismuth, the tungsten oxide. It is quite popular, but now the people would like us to use the similar semiconductors to do the other things here. So that is the case we talk about the semiconductor. You can select any one of the names you can do. So that's you can try to do is that's the application for sensors, for photocatalysis, for photoelectrochemistry, all are possible. For example, Charles Fatima has published a paper. He tries to link zinc oxide and silicon dioxide together, names that tries to degrade the organic dyes. That paper actually is very good. Okay, yeah. So he just published this paper this year. Okay, so that is the case, and then you can try to fabricate into different kinds of the morphology. So you can see that the morphology is very beautiful. Okay, you cannot just only to do one photocatalyst. You can try just to modify. Okay, we have the different kinds of cases to modify. One is tries to dope the other metal and ion. Second is that tries to add another semiconductor. Okay, all this actually is quite simple, but I think that the most important at this moment I would like us to mention is here. When you have the two different kinds of sorry, I think I need this to talk about this one. When you put different kinds of the photocatalysts together, so that you can combine with metal, quantum dots, and some organic dyes, so that they will form different kind of case. When you talk about the metal, then we call this one is the Schottky junction. If you put some quantum dots and names, then that will possibly becomes the PN heterojunction or the Z scheme. When you put the organic dye inside the names, then they will becomes the dye sensitized photocatalyst. So that for A and B and C will be very different. So when we talk about the A and B, when we talk about the puts some metal or some semiconductor, names that they will become the Schottky junction, PN heterojunction, or Z scheme. So the difference between the Z scheme and heterojunction is here. This is we have the two semiconductor photocatalyst 1 and photocatalyst 2. So that's that they have the different kinds of band gap here. Okay, and names that they will try to do the electron transfer from photocatalyst 1 to photocatalyst 2, but the whole will change will jump from photocatalyst from the PC2 to PC1. So that's the electron flow is from high to low, and hole also from high to low, or from here from the figure from low to high. So that's they will try to do the electron and hole flow different. So electron will be here, will be in photocatalyst 2, and hole will be in PC1. So that's the hole and electron can separate. So that's their efficiency will be good. We call this one is the PN heterojunction, or sometimes people also use the NN heterojunction. All this actually we call this one is the heterojunction. This scheme is something like the photosynthesis. So that we also have the two systems. One is the photosystem 1 and photosystem 2. So that's electron can jump from the photosystem 2 and names that the electron will flow to the photosystem 1 and names that to irradiate again to the excited state and names that to the other. This case actually is we learned from the tree or from those green and vegetables, okay, like algae and some others. They have these two kinds of the photosystem. So that's that they can do the photosynthesis from the carbon dioxide into the organic carbon. So we try to use these systems to do the Z scheme so that we still have the two photocatalysts. So that's the electron will jump from the HOMO to LUMO and names that's from the LUMO of the photosystem 2 to the HOMO of another photocatalyst and then jump again. So that's the electron flow is from here and names that flows to another photocatalyst and names that to names to irradiate again and names that to your acceptors. So that is the case we call this one is Z scheme. Z scheme also has two different kinds. One is the direct, the other is indirect. Indirect means that that's the needs the mediators. For example, you need some for example an ADPH or some quantum dots, some others to do. So according to the case, we can know that the photocatalyst you can design different types of your photo reaction. All these photo reaction actually you can do different kinds of the application. For example, for water splitting, energy recovers, and the names to do the environmental application. All this can do. So now I would like us to introduce you some different examples to let you know how to use it. For example, we talk about the Schottky junction-based photocatalyst. So that at this moment, the example I would like to tell you is that tries to use the copper with the titanium nanotubes. So that's there's something like here. So the titanium nanotubes is one kind of the titanium dioxide, but we try to convert into the titanium. That means that that's the unit is the TiO2, is the TiO6 minus. And names that they can form the one-dimensional. So that's from the hydrothermal measures, you can try to get the Poisson gut as the nanotubes. Microwave also can do, and name will become the nanorods, and the names you can try to convert hydrothermal and microwaves together, and the name becomes the TNT flowers. So that's you will see that's one kind of the tubes, and the names that they will get together, and names but they will have some tubes inside. And name this TNT has very good efficiencies to absorb the metal ion. I know that's some of the faculty at UII do the absorption. So that's also would like us to introduce the TNTs to you, titanium nanotube. You can see that they can absorb very huge amounts of the metal ions, copper, arsenic, even, okay, lead. You can see that for lead, that they can absorb the 0.4 gram per gram TNT. It's huge amount. It's huge amounts. Okay, yeah. So that is the case. So that you can see that that's the milligram per gram, and for lead that is really high, and for cadmium also high. Okay, yeah. So that is the case, and copper is also the case that they can absorb. So that's the absorption of metal ion by TNT. You can try to compare this to the others. That actually is that the value is very high compared to the other, even for the CNT or for some agricultures waste, that's also quite high, or compared to the activated carbon, also the case. Okay, and we also do the absorption, thermodynamics and kinetic. I think it is not so important, just skip. Okay, so when you absorb copper 2+, after the absorption of copper 2 from the wastewater, just recovers the lost material and then do the calcination again. Just means it means that I just put it in oven at 500 degrees C, and names you can try to convert copper 2 plus into the copper oxide or copper 0. Okay, so that's the here is the case. You can see that we can see some particle on the surface from the TM. Okay, we can see the particle here. We can see the particle here. And then when we use the XRD, if we calcite the copper 2 plus with TNT in air, names that they forms the copper oxide. Okay, this is the photocatalyst 1. This is the photocatalyst 2. Okay, and if we put this calcite in ammonium and nitrogen, this is for oxidizing agent. This is for reducing agent. And names your TNT and your coppers will becomes the copper 0. Will becomes you can see that here is the copper 0. So that is the case. When you use these two, just change the atmosphere. Okay, names we can produce the different kinds of the photo reaction system. For the UV light, this is the copper oxide. Okay, for the UV light, the degradation efficiency is good, quite good. Okay, compared to the P25 here, but under the visible light, it is not good enough. It is not good enough. Okay, yeah, but if you use the copper 0, no matters under the UV light is quite good, or under the visible light, it is also quite good, especially compared to the Degussa P25. So it means that when you use the TNT to absorb the copper or some metal ion first to remove the those metal ion from the wastewater, and then recover those waste and then do the calcination. Then you can convert those adsorbent into the photocatalyst. Okay, yeah, so they have two functions. The first one is the adsorbent to absorb the metal ion from the solution. Second is the recovery is the names to the calcination, and then will becomes the quite a good photocatalyst to do. So that's you can see that the area constant actually is quite high. So we also try to identify the reaction mechanism why the copper oxide cannot be done under visible light. Okay, and why the reactions can happen in cupric oxide on copper 0 and TNT. So this is the case when you use the copper 0. This is the TL2. They follow the Shakti barriers function, so that's the electron can flow from TL2 to copper 0. So that's they can separate from the electron and hole. So that's when you use the EPRs to identify the production of hydroxyl radical. You can see that's for the P25. They only can preserve for around the 30 seconds. Okay, after 1 minute, all the radical for the Degussa P25 are gone. But when it prepares our copper 0 and TNT, even for 2 to 300 seconds, that means that's after 5 minutes, they still can produce huge amounts of the radical. So it means that they can be more efficient to degrade chemical. That's because that they have the Shakti junction between copper 0 and TNT. It is the case, just to let you know. Second is to tell you that's the PN heterojunction. The case we select is the vanadium oxide with boron doped graphite carbon nitride. Vanadium oxide actually is the quite common catalyst that's in chemistry. So that's I believe that you know this one quite well. And boron doped graphite carbon nitride. Graphite carbon nitride is one kind of the relatively new carbon-based material. The case is that they have quite a good band gap at around 2.7, so that they can receive the wavelength at around 460. And if that's two-dimensional, and names that they will try to do different kinds of work here. So in that case, we would like us to see is that this graphite carbon nitride actually they can do different kind of work. Carbon dioxide photo reduction is one kind, degradation of pollutant, it is also one kind. They can also try to selective organics. The transformation is highly related to organic chemistry. They just convert compound A's to compound B's. So that's for the petrochemical reaction. It is very important. And for organics, it is also very important. Disinfection is one kind of the important in the environmental science and technology. Water splitting for energy as well as for environment is also very important. So that is the case why the graphite carbon nitride now is quite popular. In other words, no matter you talk about energy, no matter you talk about the environment, a lot of people select the graphite carbon nitride to do. Okay, yeah, so that is the case. It is the two dimension. So we try to dope it. We try to dope the graphite carbon nitride with the boron to let the electron transfers more efficient. Okay. And then we put the V2O5s on the surface. So that's the fabrication case is here. So we use the urea as the original source of the graphite carbon nitride. So that's the will become here. And then under the thermal polycondensation, and then as the boric acid calcite, and then there becomes the boron dopage, the graphite carbon nitride. Quite simple. And for the V2O5, it also quite simple. We use the precursor. Okay, use the ammonium magnetite oxide, and then with the citric acid, and then tries to then becomes the V2O5, and then we just put them together and then do the sonication. So they was on the surface, and then we use these materials to degrade some pharmaceuticals products like diclofenac. Diclofenac is one kind of the pharmaceuticals products that we widely use in hospital as well as at home. Okay, yeah. So we try to use this, and the names becomes the treated water. So that is the case. We get it. Okay, so that's you can So that is the case. We can see a name, but from the TTM, we always will see this light one is the graphite carbon nitride. A name the dark one is the V2O5. We try to do is from 10% V2O5 into 90% V2O5. So then we can get their surface areas here and then pole size here. Okay, yeah. And then when you do the optical properties, and then we can get their band gap. You always will see that their band gaps will be relatively low when we put the V2O5 together from the 2.7, and then become around the 2.3 to 2.4 here. So it means that they can receive the more energy from the sunlight. Okay, yeah. So that is the case here. We use this case for photo degradation. So that's you can see that's the photo degradation. We find that different amounts of the boron dopage also have different efficiency, but 5% is the best here. Okay, yeah. So that is the case we try to do here. And then we know that the rate constant is here. 50% is the highest one. Okay, yeah. But here you always will see that 50% is not the lowest band gap. Is not will be okay compared to 75 and 90. But when you check the surface area, it is also not the highest one. It is also not the highest. Why they can have the highest function, even though they do not have the highest surface area, also have the lowest band gap. That's because this heterojunction can let your V2O5 widely and homogeneously distributes on the surface of your polydopis carbon nitride. So that's the they can perform quite well. So that is the case. Would like us to mention when you do the PN heterojunction, you need to try to optimize your materials because you need to that this the two photocatalysts with a suitable amount so that they can do the heterojunction very well, and names that they can transfer electron on hole or carriers very smoothly. Okay, it is very important. It is very important. So that's the here we find that this one is the 50% V2O5 is the highest. When we use this 50% V2O5, a name tries to top the different kinds of the boron names, then all the case indicates that the 5% the boron topic is the best. So that is the case. We will know that. Okay, yeah. So from the case, we try this to know the environmental parameters. That's because in the real case, real environment, we have the different kinds of an ion, cation, or also some organic, so that we need to know their effect for that. So that's all these cases, that's all the ion inside. Okay, no matter for the chloride, the nitrate, sulfate, or phosphate, they all will decrease their photodegradation efficiency. That's because that they can compete the active size of the photocatalyst. But when you do the recycling, then it seems quite okay for us. And before and after the photocatalyst, you can see that their XRD patterns are almost the same. Means that they can do it again and again, and so there's really the photocatalyst. And then the efficiency won't change too much. So that is the case we would like us to emphasize. Okay, so that's the first is that tries to identify that the hormone, the position of the hormone and lumon of these two photocatalysts, so that we know that there's a band gaps position is here. Okay, V2O5 is here, and boron topaz carbon nitride is here. So that's from here when they irradiate with the visible light. Okay, and names both two can irradiate the electron from the valence bands to conduction band. Names that the electron can jump from the carbon nitride to V2O5, and the hole can jump from the V2O5 to CN. So electron will be here. So electron will be react here. Oxygens will react with electron, become the superoxide anion radical, and names to decompose dichlorogenic. Names the hole will be here. A name that tries to react with the dichlorogenic and becomes the carbon dioxide and some byproducts. So that is the possible photo reaction. They can do the heterojunction here. Okay, yeah. So the whole electrons, it seems that can circulate the layers. Okay, even though they do not circulate actually, but the concept will be something like that. The third one is the Z-scheme based photocatalyst. Names we use the case use the indirect. So the photocatalyst we select is the bismuth vanadium oxide with the nitrogen doped carbon dots and graphite carbon nitride. So we have mentioned this graphite carbon nitride, and then we talk about the bismuth vanadium oxide. That's at this moment it is quite the promising the photocatalyst because it's something like the layers two-dimensional, and their band gap actually is also quite good, around 2.4 to 2.7. Names that they can receive the visible light. And carbon dose is also one kind of the hot issue at this moment in chemistry. we can try to do the carbon dose, we can try to do the quantum dose or and some other names that they can try to top it with some other nitrogen, boron, and some other. Here we use the nitrogen top is the carbon dose. It's the 0 dimension. When we talk about the 0 dimension, means that the material is the quantum dose. And what is the quantum dose of the nanomaterial? Means that their particle size is that's named 10 nanometer. That's named 10 nanometer. 10 nanometer. Okay. This case actually, since the name is quite small, their optical and electrochemical properties will be good. So the preparation here is simple. Okay, we try to use the citric acid with some chemical we call EDA, and then tries to do the hydrolysis that becomes the nitrogen doped carbon dose. The carbon dose is mainly from the citric acid. EDA is mainly used as the source to dope the nitrogen here. Okay, so that you can see that the blue one is the nitrogen atoms, so that we can get the nitrogen doped carbon dose here. And names, you can see that for the graphitic carbon nitride, we still use the ureas to prepare, use the pyrolysis, ultrasonication, and becomes the graphitic carbon nitride. There's the graphitic carbon nitride. Temperatures for the pyrolysis will be around 550 degrees C. So that is the case. And names we put the source of the bismuth molybdenum oxide, these two together, and names do the hydrolysis, so that they will be on the surface in becomes the one-dimensional, and names to put the graphitic carbon nitride on the surface. So that's all the material we have is the NCD at the BMCN bismuth molybdenum oxide onto graphitic carbon nitride BMCN. This material actually is the two-dimensional, or suppose with one-dimensional photocatalyst and the zero-dimensional mediators. Okay, so a little bit complicated, but will be okay. Yeah, here. So this is the SEM and TM from. Sorry, the computer is just a little bit. The reaction is a little bit slow. Okay, yeah. So that's here. You can see that from the SEM, so we only can see the two-dimensional and the one-dimensional. We cannot see the zero-dimensional. But from the TM, we can see that very clearly. You can see that very clear. Okay, so from the optical properties, we can see that the color changes. Okay, especially for the narrow composite, we can see that when the wavelength, even though higher than 500 nanometers, they still can have some absorbance there. Okay, and for those photocurrent electrochemicals, you can see that when you merge together, that there's photocurrent increase compared to the pure one. So that means that when combine these three chemicals together, names that they can have the very good optical as well as electrochemical property. Names you also can see that there's impedance, there's resistance will be low, and there's production of the radicals will also quite good. Okay, so from this case, we try to identify their functional group on the surface. So this figure is a little bit complicated, but will be okay, because all is actually we only just want to identify one thing is that the three materials can merge together very tightly, and the surface is quite good because the surface is hydrophilic, so that we can see a lot of carbonyls, carboxylic groups, and the CO groups, and the CN groups. So that is the case we would like us to see here. So surface is hydrophilic, is good for us. So that we use this to degrade the ones antibiotics. We call it the ciprofloxacin, CIP. Okay, yeah, it's one kind of antibiotics. So that's here we can see that the narrow compounds that we use is quite good. Names we try to identify that they are constant, and the most importance of our research work is that we try to identify the different kinds of reaction kinetics at different pH values from pH 5 to pH 10. So that's from pH 5 to pH 10. You can see that we try to identify that's the different the constant of different species. So we use the simple concepts for environmental chemistry to identify if the CIP is the diprotic acid. So that's they will have the two different kinds of the KPA, the pKa. I'm sorry, they have the different kinds of pKa, and our material also have our own isoelectric point. So that's the surface will be positive charge and negatively charged. So that we try to identify that their rate constant for the positive charge, the CIP, or the neutron CIP, or negative charge, the CIP. So that's the tries to use the names we get here in figure D here. So that's this one is the layer zeta potential change in zeta potential of our material. But the line, the black line here is the change in total reaction kinetics, but we will know that the case here. We will know that the case that they change a lot. So that is the case we can try to identify. So that's all this we will see that's at pH 8. Okay, there's photodegradation efficiency is the best. So that is the case. We also try to know that their kinetics, especially to know whether they follow the linear hints with kinetics. The linear hints with kinetics means that they absorb on the surface first, and names the two reacts. So they will have the two steps. The first step is that the proton will diffuse not inside, onto the surface of the photocatalyst. And names that your hole and your electrons on the surface of your photocatalyst will react with those proton. So that's they have the two stages. The first one actually follow the linear absorption. Second is their reaction. So that we call this one is the linear hints with kinetics. So that's we try to do this, and the reaction is something that can be. Okay, so that's you will see that's they is quite good. So when you change the concentration of the CIP and talk about the initial rates, names that will be the good way for us. Okay, we also try to do the ions, the effects of the ions in solution, and then we always will see that for those ions they will try to decrease the photodegradations of our photocatalyst. So that is the plan. Even though they can produce some radical, but the loss radical actually is quite less compared to hydroxyl radical. We also try to use for the recyclability, and then tries to identify the radical production. The radical production is very important because here we can identify which radical is the most important. Okay, yeah, so that is the case here. That is the case here. Here's we find that that's the okay, we can jump. Here's we find that they can produce the hydroxyl radical. They also can produce the superoxide anion radical, because they can produce this two radicals. So that's we suppose their reaction mechanism is like here. So the photocatalyst 1 BM, their band gap is around 2.7. So that's they can receive the visible light at around 460 in radius. This band gap also the carbon nitride is the 2.81 also can receive small amounts of the 460 nanometer. So that's the electron will jump from the valence bands of the BMs to the conduction bands of the BM. And then the electron will transfer to our carbon dots, and then transfer to the graphitic carbon nitride, and then will irradiate again. So that's the electron will jump from the photon system 2, means that BM, and then transfer the electrons to the nitrogen doped carbon dots, and then to the photon system 1. So it's the Z scheme. Okay, it's something like a Z scheme. Until that case, hole will be on the surface of our bismuth monadium oxide. So that's that they will try to produce hydroxyl radicals to degrade the CIP. Electrons will be on the surface of graphitic carbon nitride. So that's that they will try to react with oxygen, becomes the superoxide anion radical, and then that tries to degrade the CIP. And also they can try to produce the peroxyl radical and hydrogen peroxide, and again becomes the hydroxyl radical, and then to react the CIP. That is the case we can see here. Okay, yeah. The fourth part is the PC. Okay, I still have the 15 minutes, so that's I would like us to do it very quickly. Yeah, because I hope that I can then introduce the use the flip pump. PC is one kind of the case. We not just only do the photo degradation, we try to use the material that has the electrochemical property, names with the external circuit, names that the electron can flow. So that's for the PC system is not only for the photo degradation. We have the electro system, and then have the anode and cathode. So photoanodes do the oxidation, photocathodes do the reduction. I believe you guys know. So that is the case here. So sometimes we only talk about the half the reaction, talk about the photoanode only, or talk about the photocathode only. Sometimes we combine them together, talk about the photoanode and photocathode simultaneously. So that's I just give you one example is here. Photoanode we talk about is for oxidation, so manage to the oxidation of our pollutant organic here. Photocathode is mainly from the reduction, so for photocathode manage to the water splitting to produce hydrogen gas. So that's here's that they would like us to do is to produce the hydrogen gas, or tries to produce the some reducing chemicals. But sometimes photocathode also can decompose chemicals, Okay, that is the case. So the case for the photoelectrocatalysis, we still need the photocatalyst, but we call this one is the photoelectrocatalyst. Catalyst. It will be very similar to the photocatalyst, but the band gap we used at least one photocatalyst. Their band gap should be around 1.7 to 2.4, 1.7 to 2.4 electron volts. Names that will make the PEC system more efficient. Okay, yeah. So here is the case we talk about the half reaction, especially for photocathode reaction. You use the zinc ferrite with the TiO2 and dope it on the surface of the carbon nitride. So this one is the graphitic carbon nitride, so that you can see the TM here, and then dope is on the zinc ferrite with TiO2 here. So the particle size we use for zinc ferrite with TiO2 is only around 8 here. And we do the PLC system, we find that the 15% of the graphitic carbon nitride is the base. Okay, yeah. So it is only still the experiment, and then tries to use the 0 weight percent, 5 weight percent, 10 weight percent, 15 weight percent, and 20 weight percent. Then do it. So that's you will do the PL intensity, and then you can get it. Okay, yeah. So we try to use the XRD and then use the optical property BT or use the zeta potential. I believe all these reactions you guys can do at UII, so that you also can do the same experiments here. So that's we try to identify the band gap here, okay, and then tries to see, and the surface areas will be also here. When we merge them together, there's surface area around the 97. Okay, yeah, and then the delta potential is also around the 6.5. We try to use this to do the photo reduction. So that's the here you can see that they can try to produce quite a good photo current. So when you use the ferrous TiO2 on the surface of the graphite carbon nitride, so that's there's the produced the photo current is quite high. Names we always will know that that's the one reactions on the photo cathode is that's when I have oxygen with the electron, and then we have the proton, so they will produce hydrogen peroxide, something like here. Okay, so since they can produce hydrogen peroxide, so that's they can decompose our chemicals, for example, tetracycline, one kind of the antibiotics. So here is the case, PC, photoelectros or chemical reaction. PC is here, EC is here. No matter just only for the photocatalysis of the electrocatalysis, and the reaction is not good enough. Okay, so but when you use this one, the reaction is good. Okay, yeah. So that is the case. We also try to do, but it's not the case we would like us to mention. Names we can try to talk about is the whole reaction, means that we consider the anode cathode. It is very important. It is very important for the materials chemistry. So when we talk about photoanode and photocathode name, we need just to have the membrane here, a name that tries to let the reaction very different. So that's here we try to use the NCDs, alpha iron oxide with graphite carbon nitride. Actually, this one is very similar to the Z scheme. We just change the bismuth molybdenum oxide, that's the BIMO06 into iron oxide. That's because the band gap here is quite suitable because the band gap of iron oxide is around 2.1. But for the bismuth molybdenum oxide is 2.6, 2.7 is the not good for photo electrochemical reaction. So that we just change it. We just change it. So that's the purpose is here. We try to degrade one chemical and then to do the hydrogen production. So the production will similar with citric acid, EDA, and then get the material we had. And then we just change this the preparation of iron oxide, and then that's our materials coated on the surface here. Okay, yeah. So that is the case here. So you can see that we can fabricate quite a good iron oxide, and then those graphite carbon nitride will coated on the surface of our iron oxide. Okay, so that is the case we can see. So we do the XRD BT. You can see that the value actually is not high, but the efficiency is good enough. Okay, yeah. So here is the case we can see. When we use this, the try to degrade the one kind of antibiotics, the TMP. Okay. TMP is here. Trimethoprim, trimethoprim. TMP is one kind of the antibiotics we often use in hospital. Okay, yeah. So that's here. You always will see the degradation of our case is quite good. Names we also try to do the hydrogen production from photocathode. So this part is from photoanode. Okay, difference the photocathode. Names we do the production of the hydrogen gas from photocathode. So names we do is you always will see that the degradation actually is quite stable, especially the production of the hydrogen gas are almost the same, at around of 550. Okay, yeah, so that is the kind of good. So that's the we also identifies that the possible reaction mechanism is something like the Z scheme. Okay, yeah, here. Okay, 2.1 names that's the gets the electrons to the conduction bands of iron oxide. Names that's to transfers by nitrogen carbon dose. Names that's to graphite carbon nitride, and then names do it again. So that is the case. So that means that when you want to do different kinds of the reaction of application, then you can try to select the suitable photocatalyst that you want. And most of the times they can get this in a quite a good way. All the case we mentioned actually is many from the chemicals we get from the laboratory. But not just only from the laboratory, you still can do it from the green production of the photocatalyst from the agriculture waste. Even though I have some data, but I believe that will be let you know the excellence of the UII here. So that's for all this case, I just give some example from the research of the chairpersons is Fatima. Okay, so that's we can try to use agricultural products as the reducing agent of oxidizing agents to prepare our metal oxide, our photocatalyst. Okay, that's because some agricultural products that they contain a lot of organics. Some are reducing agent like citric acid, like garlic acid, and some others. They are quite a good reducing agent. So that when you put the metal inside, they are quite easy for us to reduce them into metal oxide. Or that means that zero valence metal, or tries to oxidize into metal oxide, or use the organic parts of of your agricultural products as the carbon precursor, and the ash of the residues as the metal oxide precursors, many SL2. So that we will have this paper is published in last year's in Journal of the Environmental Chemical Engineering, and that's the Q1 journal. The impact factor is 5.9. It's quite high. Okay, this was many from the chairperson is Fatima. Okay, so he tries to use the very simple ideas to do. He tries to use the flower extracts as the green reducing agents. The names tries to prepare the tin oxide content dust for the catalyst. So that's this is the garlic acid. Okay, here. Okay, GA. Names that they can try to links to service the chelating agents as our tin ion. Names that tries to reduce into the tin plus. Names that becomes the tin zero. Okay, that means that to the reducing agent. But sometimes that they'll try to oxidize when we do it under the aerobic condition. Names that they will become from the tin zeros to becomes the tin oxide. So that's the particle size will be very, very small, will be very, very small. She did quite a good work, and the names that we will find that even those that they try to the dust and the name with the hydrogen peroxide and without the hydrogen peroxide, that they also have to find a bit difference. Okay, yeah, and also defines the different pH value here, and also tries this to identify. The paper published till now has been cited for 13 times. It's quite good. It's quite good. So that means that the quality of this paper is quite high. So that is the case original work from UII. And second papers published in this year, he tries to use bamboo leaves age as the source of SiO2 because for most of the agriculture's waste they contains the difference amounts of the silicon dioxide. So that's the heat tries to do that. When you burn out all the organics, and lost age actually contains the relatively high concentration of the silicon dioxide. So that's the he used the bamboo leaf ash as the source of the silicon dioxide and tries to push the zinc acetate as the precursor, use the sodium methods to mix up these two together. So that's the when you use the different ratio, you can see that's the morphology changes. So very beautiful cases. So that's the for the pure SiO2, you can see that the TM is here, and then put the 5% in oxides on the silicon dioxide, so that you can see that the particle size also changes. He tries to use the these materials to do the photooxidation of the rhodamine B, one kind of the organic dyes, and tries to do the recycling. Okay, you can see that it's very stable. And he compared, she compares the result with some reference data. And here you always will see that there's degradation efficiency 99.3 is much higher than the other papers. Even there's a K value is also high compared to the other. It means that even though you use the very simple ideas just to prepare your photocatalyst from agricultural waste, no matter you try to use this as the reducing agents or tries to use as the raw material. If you can select the proper material and names, then that will be good way. Okay. It is also highly related to circular economy and also highly related to agricultural waste reutilization. So you can try to fulfill the SDG and net zero emission. So it is very important. So idea is there, material is there. So the conclusion is here. Climate change, water, energy, food, and carbon, or some materials will be the most important issue worldwide by 2050. So you guys need to have the ideas, talk about the case. It is very important. Okay. Names, if we would like us to do in chemistry, okay, no matter for the future or the motivation or the now is ongoing, food, energy, water, for the field or when. It is very important. You need to design your own. Try to find your niche in your fields. No matter you would like to do the environment or to do the energy or do the pharmaceutical, food chemistry, all are okay. But all are highly related to those concepts we mentioned. Tries to develop your own material, no matter from agricultural waste or from the different kind of raw material. Tries to find one and tries to combine them together. If you like to do the water purification and the hydrogen production of energy application, name photocatalyst and the photoelectrochemical nanocomposite will be very important. Okay, that's my talk. Thank you for your attention.
Much, Professor Rian, for insightful presentation. It was very nice and inspiring topic, especially for students and lecturers in conducting the future research to face the issues challenge by 2050. And now there are already several questions regarding your presentation in chat room. Maybe before I read the question, I will give the time for the participant who wants to ask directly to Professor Rian. Is there any? participant who wants to ask directly. So you may unmute your microphone and activate your video to ask
Really?
to
I
Professor.
no, I think just now the voice is still okay, right? I just stop the sharing of the screen. So that's because the voice here from my computer is not so clear. So that's the main, yeah.
Yeah, that's clear enough, Professor. Okay. So if there's no participants who wants to ask directly, maybe I will read the question from the chat box.
Okay.
The first question is from our student, Nevi Indriani. She's very interested with your topic, and she has two questions here, Professor.
Yeah.
The first question is, as long as emission cannot be released into the atmosphere, only plants are needed for photosynthesis. How can you solve the global issue? And for the second question, emission capture technology is one of the net zero emission options. Have developed country implemented this technology, and what's an example of that?
So that's the here. Oh, the lot will be good. Thank you. So that's the as long as the emission can last. So that's the protest and that is. Okay. This is the very big questions and also quite a good. Actually.
I'm sorry, Professor. You just
okay. Okay.
Thank you.
Can you hear me now?
Yeah.
Okay. So this is quite a big questions and also quite a good questions. The emission of carbon dioxide at this moment that cannot be stopped because we need some energy. So we need like I mentioned, we need to do is in parallel. One is that tries to control the emissions of the carbon dioxide, but we still need to remove the carbon dioxide from the atmosphere. So the case that now we would like us to do is try from the government or from the international or work tries to do not use the fossil fuel. So that will be good for us to reduce the emission of carbon dioxide. But for the removal of the carbon dioxide in the air, we really need the photosynthesis, not just from algae. We need this to try this to cultivate tree, become a forest. So that will be the huge amount, but it takes time. So that is the reason why now is 2020, why we set the goal on 2050. So now we are doing two ways. One is tries to ban or to minimize the use of the fossil fuel. Okay. Second is we try this to cultivate. We call this one is the carbon sink. So that is the one kind of the concept for carbon farming. Okay. We have the trees, we have forests, we have some weeds, the vegetable and some others. They all can reduce carbon dioxide, even though the amount is small, but the land is huge. So that's the total amount is also quite huge. But we cannot let lose carbon dioxide inside the plant converts into carbon dioxide. So that's when we eat also the residues that needs to convert into some material or some high value added products. Okay, yeah. So that is the case. Second is that the emission captures technology is one of the net zero option. Have developed country implements that yes, they do is very extensive and heavily in the US, in in Japan, in Europe, they use a lot of technologies to do the CCUS or CCSU. Yes, they do it. Theoretically, they have the two different kinds. Because it is not the topics I would like to mention today. They use adsorption or absorption. Adsorption, they try to develop some solid adsorbent like calcium oxide. So that when you have the CaO plus CO2, and then they will become the CaCO3. So that is the case that they would like us to do. Second is that the carbon dioxide is acidic gas, because they have the pK 6.3. So that's that they use the amine as the adsorbent liquid. Okay, so that's the carbon dioxide will dissolve inside so that they can absorb. So that's that they have commercialized those case. So they have done that quite good. Okay, yeah. And the other is that, thank you. I have the question how to prevent this. That's the big issue. How to prevent the deforestation? That depends on the government. Okay, I have no answer here. I have no answer here. Some country needs the lands for people to live, but we can try to use the like I mentioned again. We can try this to cultivate tree and then become a forest into those the lands that is not suitable to plants to cultivate the tree. We need to use some technologies to do that to improve the soil quality. Okay, now a lot of people are trying to do so. That is the case. But unfortunately, I do not have answer how to prevent, because it's highly related to every country is policies. Okay, yeah. How to capture the carbons naturally? Only for bio. So that's for tree, for plant, for algae. That's the case. Okay, yeah. Otherwise, we can use some technology like I mentioned. Use the CCSU. Okay, use the adsorption or the adsorption. Okay, yeah. So that is the case. Okay, yeah.
Okay, thank you, Professor. And maybe due to the limited time, we have the last question is from Rahmi Ahdiati. Professor, I wanna ask about various metals such as mercury, cadmium, titanium dioxide, which are added to the carrier for various environmental treatments. If it's no longer carried out on the lab scale, how to manage so the metals doesn't become a new problem in the environment? Thank you.
Okay. Actually, we do not add any mercury and cadmium inside the material we are using, because these two material is very toxic. So that's the no matter you are in the fields of environmental science and technology, or you are in the areas of the chemistry, we don't use the mercury and cadmium, especially when we want to use it. The first thing is that it will be toxic to the user. Second is that all the material actually they will release a little bit, even though only 0.1% or 0.5% in total after the use. But the concentration of the mercury and cadmium is very toxic. 0.1 means that's the 1,000 ppm. If you just put the 1% inside, okay, I mean that's the total mass. If you just put the 1% inside, they still have the 1 ppm. 1 ppm mercury and cadmium actually is really fatal. So that's that we don't want to do that. We will use the more environmental friendly. Okay, yeah. So that is the case we would like us to do. For example, we would like us to add the iron inside. We have added the mechanism inside. We will add some others environmental friendly, and we use this transition metal, iron, nickel, and some others to absorb the trace amounts of the mercury and cadmiums in the environment. So it is a different kind. So we do not add the mercury cadmiums in our carrier. Instead, we use the most environmental friendly transition metal as the dopant get inside the material to absorb mercury, cadmium, and arsenic. For example, we will use the iron 2 as the gut absorbance for arsenic. Okay, and we will use the sulfur as the gut chelating agent for mercury. Okay, so that is the case. So, okay, yeah, so that is the case. Thank you. Yeah.
Thank you very much, Professor Ryan. I think that's all the question that can be answered by Professor Ryan because of the time is almost over. So we can close this session. So ladies and gentlemen, this is the end of the first presentation. I'd like to say thank you very much for Professor Ryan. We really enjoyed your talk. That was very inspiring. Hopefully we will have another opportunity to conduct some collaboration in the future. And ladies and gentlemen, thank you very much for your contribution in this session. Now I'll give back the time to Mrs. Salma Haminati, PhD. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, Prof.
Thank you. Thank you. Okay.
Thank you, Prof. Riandong.
Thank you, Prof. Jong.
Bye-bye. 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 Bye-bye.
Oh, please wait for a minute, Professor, because there will be honorable certificate that we have to give to you.
Okay, thank you.
Thank you. Okay, thank you very much to Professor Riandong. It was very interesting talk, and we have a certificate for you. Please, please. Thank
Perfect.
you.
Very beautiful. Thank you.
Thank you.
Thank you.
Thank you.
Okay, bye-bye.
Bye-bye.
Bye-bye, Prof.
Bye-bye. Bye-bye.
See you next.
Prof.
Thank you.
Bye-bye. Padimas, you really do a good work. Yeah, yeah.
Thank you.
Lost data is very beautiful and quite good. Yeah.
Thank you very much. Yeah.
You are welcome. You are welcome. Okay. Yeah. Okay. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye. Bye-bye.
Bye, Prof. Have a nice day. Thank you.
Yeah. You too.
See you tomorrow.
Have a nice day. Bye-bye. Bye-bye.
Okay. Okay, ladies and gentlemen. Next, we have a lecture again on this about the research in Master of Chemistry Studies program. So before this session start, I will deliver this session to the moderator. Please, Miss Ikayanti, Master in Science.
Okay, terima kasih. Thank you very much, Dr. Salma Haminati. Can you hear me? Hello?
Yes.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon, everyone. I'm Ikayanti and the moderator of this session, second session. I'm very pleased to see you here and welcome all of you to this Studium Generale The Studium Generale today is about recent research in chemistry, progress, and motivation. And the second speaker is Dr. Andes Alwar, MSc, PhD. And please, I want to read this curriculum vitae. Dr. Andes Alwar, MSc, PhD, is the chair of the master program in chemistry, Universitas Islam Indonesia. And baru 2nd May 1962. I hope I'm not wrong. Dr. Andes Alwar, MSc, PhD, complete his bachelor degree in chemistry at Universitas Riau, Pekanbaru, Indonesia, and the master degree in organic chemistry at Howard University, Washington, D.C., USA, and the doctoral program in environmental chemistry and material science at University Sains Malaysia, USM, Malaysia. And his expertise in organic chemistry and activated carbon gas chemistry. And today, Dr. Andes Alwar, MSc, PhD, will talk about research in Master of Chemistry Study Program in Universitas Islam Indonesia. And please welcome Dr. Andes Alwar, MSc, PhD. The time is yours. Thank you.
Okay, thank you, Bu Ika. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, can you hear my voice?
Yes, yes.
Okay, it's clear, okay? Okay,
Yes.
thank you very much. Sarapan pagi dengan ketan, setelah itu mencuci kain. Dengan senang hati saya ucapkan selamat datang para hadirin di Fakultas MIPA. Okay, this session I will talk about the recent research in chemistry, progress, and motivation. Okay, before I start, I should honorable to the Dean of Faculty Mathematics and Natural Science, Prof. Rianto, and the Chairman of Department of Chemistry, Prof. Ispatimah, and all moderator and audience. Okay, air mata jatuh berderai karena menonton film Korea. Dikarenakan audiens sudah ramai, oke, mari kita mulai saja. Oke, that form from Indonesia or Melayu style ya. Okay, welcome to Universitas Islam Indonesia. Yeah, you can see this. You can see the picture here. Universitas Islam Indonesia, the main entrance to the UII, and the right side is the library. It's a very nice library. We have 4 floor library, and then the right side up of the library building, we can see student for the undergraduate students. So UII, University of Indonesia, receive around 5,000 students each year. And then in the middle, our building, Fakultas Mathematics and Natural Science, Fakulty Mathematics and Natural Science. This is the MIPA. Okay, let I continue. First of all, Universitas Islam Indonesia has been established on the 8th July 1945, with the first name is the Sekolah Tinggi Islam or Islamic Higher School located in Jakarta, and then the name of STI or Islamic Higher School has been changed to Universitas Islam Indonesia or Islamic University of Indonesia. Now located in Yogyakarta, exactly at the north of the Yogyakarta, Sleman, on the Kaliurang route. Yeah, it's about 14 kilometers from the north of the Jakarta. The founders of the UII, Dr. Muhammad Hatta, K. Haji Wahid Asim, Abdul Wahab, K. Haji Abdul Wahab, Dr. Satiman Wirjo Sanjoyo, K. Haji Abdul Kahar Muzakir, Muhammad Nasir, K. Haji Mas Mansur. Okay, this is the founder of in UII. UII right now become a leader in the private university in Indonesia. Okay, roadmap of the magister chemistry. Yeah, so this roadmap has been designed carefully by the team, including lecturer, user, industry, or university, student. So we have a program starting from the 2020 and until 2040. So this department has been established 2018. So right now we have about 3 years. Yeah, we have 3 years. So the main object of our program is how to be the best master chemistry in Indonesia. That's our program. And now we have accredited by BANPT, and also we are processing accredited by ASEAN from German. Hopefully in the end of this year, maybe next month we will get the result. Yeah, hopefully our department can be accredited with the international accreditation. Okay, now further study in chemistry. Yeah, find your experience or find your research area in one of the research excellencies in a magister chemistry. So there is a quite different our department with the other chemistry, magister chemistry, and other faculty in Indonesia. In our department, we have separated 3 departments or 3 concentration. The development of the essential oil and derivative and material for energy and environment, and development of the natural product for health and food. Yeah, all these departments under physical chemistry, analytical chemistry, inorganic chemistry, biochemistry, organic chemistry. So we study multi-discipline in chemistry. Yeah, multi-discipline. So every student that want to study in this department, they have to choose one of these concentration according to this what do you call it? To this hobby, bro. Yeah, to this hobby. Okay. Let me see one by one of this concentration. Yeah, the first one, development of essential oil and derivative product. In this department, focus on the professional and in-depth study of essential oil and their derivative product. So in this department, the student or research can be focused how to prepare oil, yeah, or essential oil. So can be prepared from many type of plant. The content consists of the containing essential oil. Some of the products like eucalyptus oil, peppermint oil, citronella oil. This product has been obtained in our laboratory and also has been developed and applied in many products such as soap, perfume, massage oil, and many other products. And now we know that trend opportunity of the forecast in essential oil to 2025 is very, very good. They steadily increase. It means the essential oil is very important for the future. And then the second, the development of material for the energy and environment. Research in material for energy and the environment focus on development of material from natural and synthetic material like zeolite, clay, activated carbon, and many other. Yeah, composite also. Yeah, and recently research in this department focus on the catalyst. Yeah, such as a photocatalyst. Just now, Riandong has widely described about the photocatalyst. Yeah, Riandong is one of our lecturer in this department. So in the material department of material. Okay, and then also design the catalyst for the hydrocracking. Yeah, heterogeneous hydrocracking, and isomerization, and also for absorbent that used for wastewater treatment. And then the third development of natural product for food and health. Yeah, this one of the development of product that are used for the food and health. And each of the department, yeah, have a qualified lecturer, yeah, in our department, like the department of essential oil and energy for derivative. Our lecturer, Prof. Rianto, Dr. Dwi Arso Rubianto, and also Dr. Nur Fitri, and the department of material, Prof. Is Fatima, yeah, including me, Alwar, and then many other lecturers like Gani Purwondiono and Dr. Maisari Utami, and natural science like Dr. Yulianto Tatang Sabut, Dr. Habibi Hidayat, and Dr. Nur Fitri. So all the lecturers are good qualified in the field, each field. Okay, why are research skills important? Yeah, research skills are a vital part of the writing process because they enable writers to find information to create outline for the writing project. So students in our department, they have to do a research, and then research, the result of research should be published in international publication. At least they submit the result of research in the international publication. So that's why we give a chance to the student to be a good skill in research. And then how to improve the research skill? Okay, let me see that. When the students start to write a short story, it means you will likely reach a point in your first draft where you don't have where you don't have enough information or data to go forward. So that's very important. Now, that's very important statement. When you write something, it means you have good draft for the research. However, it doesn't have enough to come forward. Okay, let me see. Develop an action. What should we do? Yeah, just for the student, what should we do here? All students should be figure out what will you do. Yeah, you figure out what will you do. You have to evaluate yourself. Have you done a research according to your project? Okay, well, so or you have to read so many information about your research. And then go to the second step, identify an area of focus. You have to more focus with the wide information, and then you make a focus to small information. In here, you will find the state of art the research. Yeah, you will find the objective of your research. You will find how to do a research, including the tool or instrumentation. And then the next step, the collecting data. Collecting data is experiment, systematical experiment. Yeah, you have to find the good data by the tool or by instrumentation. Let me say the NMR, gas shock analyzer, UVV or FTIR, NMR, HRT, many other instruments that we have there. Okay. When you do not have enough data, you should return to identify the area. And you have to evaluate again until you have a good data. After that, go the next step, analyze the interpreted data. Yeah, so analyze the data. You try to find the good answer that you have created before the research. Yeah. You should find a good answer to do the data from the data. What do you do after that? When you have data. You try to figure out by figure, by table, many other methods that can be used to interpret data. When you have good answer, all the answers you have created at the first time, and you can continue to good result. Yeah, it means you will have a good result. So then when you have a good result, you have to make a report, and then you have to publish. This is our program in the department. Okay, 6 tips for improving researching skill. Actually, there are many tips for improving researching skill. There are many, but in this moment, I will tell you about 6 tips. Yeah, the first time, start broad and then dive into the specific. Yeah, what should you do here? Research is a big task. Yeah, so it can be overwhelming to know where to start. Sometimes because the big information we will not we do not know where we want to start our research. That's very important. Okay, so that's why there is nothing wrong with the basic internet search to get your start. So you can find any source of the information. Yeah, Googling. Okay, just Googling. Journals, there are many journals. Yeah, but sometimes some of the information from the Googling media like Wikipedia is not accurate. Yeah, it's not accurate. Sometimes not accurate. So you have to find the good one. Yeah, while not always accurate, are a great way to orientate yourself a topic, since they usually give a basic overview with a brief story and any key point. So it's very important. Yeah, it's very important to read so many sort of information, find some many sort of information, and then study deeply. Yeah, focus what will you want to do. And then the second, learn how to recognize quality of sound. Yeah, as I told the first time, so many information and so many good information, and then you have to recognize which one information that you want to do, right? Use the critical analytical skill or critical thinking. This is very good. So after that, yeah, you can recognize the good source from not the good one. Okay, so after that you will get the good information. Okay, and then verified information from several sources. Yeah, the internet is a big place. For the most part, everyone can say whatever they want online. Yeah, so many information sources. Yeah, website, for example. The best way to combat this, make sure that whatever to find your research, several different sources can verify, oh, that is true. To make sure the information that you get is true. Okay. So this is very important for the student to choose the right information from the wide sort of information. Okay. Okay. The fourth, be open to surprise answer. Okay. Good research is all about finding answer to your research question. Okay. So many questions that we find in the research. So don't close your mind with the question. You should open your mind with the question. Yeah. Keep open mind so that you will learn as deeply as possible. Yeah, this is very important for the student. Okay, open your mind and retrieve all the question, and it is better you can answer all the question. Okay, okay, and then the 5, stay organized. Yeah, stay organized. during the data collection process, you will be seeing a huge amount of information from web page to PDF to video and many other. Yeah, it is vital that you keep all this information organized in some way to prevent yourself from losing something or not being able to cite something properly. So that's why when you get data, you have to combine with other data. Although you feel your data is correct, but you have to combine, you have to compare with the other data. Okay, it's very important. Yeah, so there are plenty of ways to keep your research project organized, but there are a few common ones. Bookmarks, very important. In your internet browser. Yeah, sign the data using the bookmark, index card, and annotate bibliography that are keep updated as you go. So when you get data, please recognize and bookmark. Yeah, in order your data do not lose. Yeah. Okay, the last one step is the advantage of the library resources. So if you still have questions about the research, don't worry. Yeah, there are plenty of places out. There are to help you out. Even you are not a student doing academic or course related to research, you can use a library. Yeah, you can use to find a good answer. Okay. One way to find a good answer in the research. Okay, these are 6 tips that can be used for improve your research. Yeah, motivate your research, especially for the magister student. Okay, the next slide. What should we do? Yeah, here we are in the magister chemistry program study at MIPA. We have a very nice instrumentation, a very accurate instrumentation to support all the students in the research program. Yeah, in our department we have the same ADX. Yes, very nice information to study about the the morphology structure. Yeah, this good for the organic or inorganic. Yeah, also we get the NMR. Yeah, for the student about we have a 60 megahertz, if I'm not mistaken. Yeah, and then we have also PSR, foresight analyzer. Yeah, this very nice information instrumentation for the material. Yeah, and also we also have a UV visible, a single beam. Yeah, to support the student in the finishing their project. And then we also have a HRD. Yeah, so for the material is very important, this implementation. GCMS for the organic, for the natural products. Yeah, HPLC. Yeah, so we have also this gas stop analyzer. Yeah, Quantachrome. Yeah, it's very nice to study the BET foresight analyzer. Yeah, to study the micro or mesoporosity. Okay, we have also this FTIR. Yeah, FTIR, and then RS, and many other, some other instrumentation we also have in our laboratory. What does it mean? It means this department is good qualified to do the magister chemistry, and we will support the all students to be finished in 2 years. Yeah, 4 semester. So I think it is very good chance for the student just finish undergraduate chemistry or finish in the pharmacy or biology, yeah, or educational chemistry. they can continue the study in our department, chemistry, magister of chemistry, with the low cost of the tuition fee. Okay, and also we offer some of the scholarship, yeah, scholarship for the student. Okay, I think that all is my talk. So let's join with us to share knowledge in the chemical science. Thank you very much, Bu Ika. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Ades Alwar, MSc PhD, for the explanation of research in Master of Chemistry Study Program, Universitas Islam Indonesia. And then, well, everyone, now we are come to the question and answer session. If there are participants who want to ask directly to Dr. Ades Alwar, MSc PhD, please raise your hand and don't forget mention your name. Please, any question maybe? Or maybe you can using in bahasa.
Yeah, that's right. Just now I prefer to speak bahasa Indonesia because I got information from the team, no one from the overseas, the audience.
Especially for
ya lebih baik bahasa Indonesia.
Ya, mahasiswa kimia.
Satupun dari luar negeri.
Yeah. Any other? Okay, maybe Mr. Alwar, study program also for students to collaborate with supervisor from outside the chemistry study program. Success institution or government or non-government agencies. Halo, Pak Alwar?
Ya. Yeah. Okay, any question?
This is any question for Amri Yahya.
Okay.
Many students have a such feeling negative toward research paper. Do you have any suggestion that you could share that help reading research paper more manageable?
Okay, research paper is very compulsory in our department. So every student should have a research paper from the result of the research project. Okay, so for the first time, we hope that the student can submit the paper into the journal with the accepted paper. However, after we got the information from the ASIIN from German, it is quite difficult to find to get the accepted paper because it takes long time and spend much money to get the accepted paper. So that's why we decrease the requirement by submitting the paper to the international journal. That's I think. Is correct like that? Yeah. Pak Amri, Mas Amri.
Mas Amri. Hello.
Okay. Yeah.
Yeah.
So is it compulsory? Yeah, it is compulsory for the student. All the student must have a research paper, journal. Yeah, journal.
Okay, thank you, Mr. Awal. And then the second question from Rina Maulina. How to choose the right concept or topic in research to be in line with current uses?
Okay, yeah. This is that's why we for the first tip just now. So before we start the research, you have to read a lot of information. Okay, you have to read a lot of information. So many information, and then what kind of what is your topic? You can find the topic after you read many information, right? And then after you read many information, you have to focus one topic. Yeah, one topic. What will you do? And then you can create some question, yeah, with the topic. You can see, we can see the condition right now. Probably there are research with the same topic with you, and you have to create what is the difference with the previous paper. Yeah. So with reading the many information, and then you compare with the other paper, you will have state of the art, the novelty. Yeah, the novelty. Yeah, it's very important. After you get the novelty, so we can run the experiment. You find the objective, you find the method, you find you can predict the result. Yeah, you can predict the result. Something like that, Mbak Ika.
Okay, thank you, Mr. Awal. And then I have a question for Chemistry Master Study Program. And does the Chemistry Master Study Program also open up opportunities for students to collaborate with supervisor from outside the Chemistry Study Program?
Yes, of course. Yeah. For example, if any student they has work in other province, and then we can collaborate with his department, with his department. The student can do a research in the department. Yeah, if there is a good qualified what do you call that, supervisor over there, so we can ask him as a supervisor, the second supervisor. Yeah, of course we can do that.
Okay, thank you, Mr. Awal. And then any other question for Dr. Andes Alwar, MSc PhD? Any question? Hello? Okay, maybe if there's no more question, we can enough for this session. And the conclusion, thank you very much for Mr. Awar for the explanation, explain your presentation. And the conclusion in this session, the Master of Chemistry Study Program in Universitas Islam Indonesia has 3 research excellencies. And the first, the development of essential oil and its derivative product. And the second, the development of material for energy and environment. And the third, the development of natural materials for health and food. And for the new student, you can choose the research excellencies according to their interest and expertise. And thank you very much for Dr. Andes Alwar, MSc PhD, and all of the audience for active participant today. And hopefully the Studium Generale today will give benefit for us. And thank you. And I will give it back to MC. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much to Mr. Dr. Andes Alwar, PhD, for nice talk, and it was very interesting. And we will give a certificate to you. Wait a minute. Okay. Before this close this event, we will have the announcement. So the person will give door prize in the first session is Nevi, Febi, and Rahmi. So congratulations. Then the second session, the person will get the door prize is Rina Maulina Amriyahya. Okay, so congratulations. Okay. Actually, we have participant from abroad. I think Mr. Binyamin. Hello. I just saya. Oh, okay. So okay, he didn't give the response. Okay, so next I will show the information for the engineer tomorrow. Okay, so we have this workshop. Please come again tomorrow around at 8 or 8:30, and we will have workshop and clinic of writing scientific article, and we will enjoy it. Thank you. So, at now I would like to close this session. Please say Alhamdulillahirabbil alamin, and thank you very much for the speaker and participant. I hope you enjoyed too much, and so if I have a mistake, I apologize. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh.
Oke, terima kasih semua. Thank you everyone.
Terima kasih.
Terima kasih. Sukses selalu.
Sukses untuk acara besok.
Terima kasih, Pak. Jangan lupa acara besok.
Terima kasih.
Acara besok masih seharian.
Ya.
Semangat.